Professor, I have a question on the lab that's due on Saturday.
Yes, Christine.
Um, there's the same equation for percent moisture and percent yield in the apple
Mhm.
dehydration lab.
Mhm. Yeah, actually the yield equation was wrong. That was from previous year, and I didn't check. So the yield equation should be equal to the final weight of the apple divided by the initial weight of the apple. So because the yield means how much product is left after the drying process. So the way it was calculated basically was calculating the weight loss, which is apparently not correct.
Okay, cool. Thank you.
I mean, even because it's my mistake, I didn't read it through. It was from previous year's material, so I think even though you used the old equation to get the wrong number, I will just correct you, and I won't take any points off.
Okay, cool. Thank you.
Sure. Okay, let me share my screen. Okay, so this class is about the food concentration or evaporation. Oh, let me see. We're missing about 10 students. I'll just wait for maybe 1 minute because people are still coming. Oh, 31. Okay, 32. Okay, never mind. I'll just start here now. Still, we're missing like 8, 9 students. That's okay. All right. So yesterday we had our no, last week was no 2 days ago we had our second midterm exam. The average was 86.5. The highest was 98. A little bit lower than the first one. The first one, the average was about 89 because there was extra credit, so that was a little bit higher. But anyway, the average is a little bit lower. And the other reason probably is that I didn't post another quiz for the drawing lecture because I thought there were one assignment and then one lab report that you guys are working on, and I didn't want to add too much uh, work at the same time. So I guess that's part of the reason that you lost some points in the drawing related questions. So, but I think 86.5 is somewhere within my expectation, and we have very good students get close to 100. Many students got above 95. So overall, I think it looks pretty good. If you have questions regarding the exam question, or if you feel the grading is not is not appropriate, or you want to something that you should have gotten, you should have received the score, but the points, but I didn't give the point. Just let me know. We can discuss about it. And for the final exam, finally I checked with the department. Basically, the final exam time is not determined. I basically I don't have any choice in terms of time. Everything is arranged by the university according to the lecture time. So in our case, our lecture time is 5:10 to starting at 5:10 p.m. Tuesday and Thursday. So in this case, our final exam will be on Friday, March 19th, 7:10 p.m. to 10 p.m. So this is the last time block for taking finals. But the good thing is that you'll have more time to study. But the bad thing is that you have less time to take a rest for the break. But anyway, this is what it is. Okay, so for the lab 4, we just posted the video and the data on the canvas. So you guys can start writing the lab report. If you have any questions, come to my office hour. And the lab report will be due next week, a week from today. And also the quiz 7 will be posted tomorrow or tonight, maybe around midnight. Will be due next week, next Thursday, a week from today as well. So any questions about the announcements?
Did you say that the final was cumulative?
Yes.
Okay.
So the final, right now I'm thinking of not using Zoom. I just posted as a timely, like a 3-hour block assignment. Then you guys can just work on it, and because I feel like the Zoom thing is, although many professors they use Zoom to kind of make sure no one's cheating, but in my case, I don't think anyone's cheating in this class. So probably I'll let you know guys later before maybe a week ahead of time, making sure that we are using Zoom or not. But the exam format will be pretty much the same. Will be 80% of multiple choices and 20% of calculation and short answers. Should be straightforward. All right, so moving to this lecture. A brief content the content we'll cover in this lecture. Basically, we'll talk about the food concentration, and we'll emphasize on evaporation for this lecture. So we'll go through the definition, the classification of food concentration, and the definition of the food evaporation, the concept and the calculation of sensible heat and the latent heat. And we'll also learn about a single and multi-effect evaporator. I did cover this very briefly in the unit operation, for the unit operation in the first couple of weeks. But here we're going to go more in depth. And also we'll discuss about different types of evaporators and learn a little bit about mass balance during the evaporation. So it's a quite heavy class. I hope we can finish within the time limit. So classification of food concentration. So as you guys have learned about the food dehydration, so basically we remove all the water, but in the food concentration, we are just removing partially, maybe like 50%, 60% of water, not nearly all the water. Okay, so there are two ways of doing the food concentration to remove water. One way is to use heat. For example, there are evaporation and distillation. And the other way is to use non-thermal approach, like reverse osmosis, ultrafiltration, dialysis, and freeze concentration. So we will focus on the thermal concentration this lecture, and we'll cover the rest of the non-thermal process in the rest of this quarter. So this is just a brief diagram for membrane separation and non-thermal approach. Okay, so I'm going to skip here because I'll cover in pretty much more detail in the next few weeks. And also the freeze concentration. So it's also a non-thermal process. All right, so evaporation is something that we'll focus on today. Those are all the evaporators. You can see they're huge. They can be scaled up. And right now you may not, you might be curious, why do we have to build it so high? But after this lecture, you'll probably understand why we want to build it vertically instead of use like a horizontal design for those evaporators. So definition, so the evaporation is a unit operation commonly used to remove water from dilute liquid foods. So there are a few keywords. It's a unit operation and it's to remove water. If it's not water, then it's called distillation, right? Sometimes we use distillation to concentrate alcohol products. So evaporation is targeting at water, and the feed is the dilute liquid foods, and the product is the concentrated liquid products. And remember, it's still liquid, and there's heating, okay? And the purpose is to reduce the volume of the liquid foods so that the storage and the transportation costs can be reduced. And also we are trying to increase the solid contents so that the water activity can be lower if we have more concentrated sugar or salts. In that way, we can inhibit the growth of microbial. So these are two main purposes. Okay, so last week we had our lab on the tomato processing, and so to make a tomato paste, we need to concentrate tomato juice, for example, 5 to 6% solids using evaporation, and to concentrate them into 35 to 37% solids. It's very typical for the tomato paste. And also we do for other food products as well. So this is a diagram that I showed you guys last week during the fruit and the vegetable processing. Basically, the tomato, this is the flow chart to prepare the tomato paste. And in our lab, we use the cold break and hot break to make a juice extractor. But we didn't go through evaporation process because that will take a long time. So the evaporation is basically something we use to further concentrate the tomato juice. So it's a very important step in food manufacturing. So beyond the tomato paste, can you guys name a few that you have found in the grocery store? I just realized that the last time when we had this discussion, I saw someone typed in the chat box, but I didn't notice. At the end, after the class finished, when I closed all the windows, I saw someone typed their answers. And I'm sorry that I missed the chat. If I missed any chat, because there are a couple windows, I always get blocked. If I missed your comments, just to unmute yourself and shout out. Okay. All right. So any food products that you have seen in the grocery store that you believe it's made by evaporation?
Evaporated milk.
Yes, evaporated milk. Are they usually in cans or in bottles?
Something like
yes,
better than bouillon.
Yes, that's true. Anything else?
Probably most syrups.
Yes, a lot of syrups too. Syrup like corn syrup and high fructose syrup. So yeah, I also found very similar products. One thing quite special is the condensed cream of chicken, like a chicken broth Some of them, they are highly diluted, but some products, they are highly concentrated. So if you buy those condensed soup, you can use it for more times in the cooking, right? So those are just representative products that we see. So it's quite a lot, but maybe not as many as the dehydrated products. So evaporation, there are two. So there are two main ways that we do evaporation. So at home, if we want to condense something, we use the very simple bowl evaporation, right? We just heat up the product using flame or using the hot plate, and then the water will evaporate. And but in the industry, actually, we use a very efficient heat exchanger. Like here, it's more like a plate or tube heat exchanger. So the steam and the food product can contact with each other in a much larger surface area. So the residence time can be reduced. So when we are evaporating water, actually the water will go through several phases. So when the first stage is that we are trying to heat up water from room temperature, which is about 20 degrees C, to a boiling point, which is 100 degrees C. So in this stage, the water is in a liquid stage. And then we need to keep adding input energy to remove those water during the boiling process, right? So this is, in this process, we generate a steam. And then finally, when all the water becomes steam, if we keep adding input energy, the temperature of steam will keep increase. So this is how steam is generated. And in our evaporation in the industry, the steam is actually the heat source that we use to evaporate products. So the steam actually provided energy for the food to remove water. So there are several different heat types. During the liquid phase, the heat that absorbed by the water is called sensible heat. And then during the boiling, during the boiling or the vaporization process, the heat we call it the latent heat. And then after all the water becomes gas, steam, if the temperature keep increasing, then again it's sensible heat. So sensible heat, if I want to generalize the terminology, is the heat that we use to increase the temperature of water, right? And without any phase change. But the latent heat is the heat that we use to change the phase of water without any temperature difference. So that's their differences. Is there any questions about the concept? Because we'll do a little bit of calculation on this energy balance. Okay, so I guess many of you might have learned it in the physics classes. So here's the equation that we use to calculate the sensible heat. It's the heat that used to raise temperature of the food. And then usually we use the term QS to represent latent heat. And this term is equal to M, which is the mass of the water, times CP. CP is the specific heat of the water, and times the temperature difference. So basically T2 is the final temperature and T1 is the initial temperature. While in the latent heat, the equation is different. and we noted the latent heat using QL, and it's equal to M, which is the mass of water, times the lambda V. So lambda is the specific latent. So those terminologies will give you in either exams or quiz or assignments. You don't have to find it. Actually, there's a very complicated table that you can find all those numbers based on the, just like a psychrometric chart, but that will be covered in like 330 or 440 higher level of the food engineering courses. Here we just give you the number for you to calculate. Okay, let's do a quick practice. So the question is, what is the heat requirement to increase 10 kilogram of water from 25 to 100 degrees C, assuming there's no phase exchange, no phase change? And the specific heat Cp of water is given at 4.2 times 4.2, and then the unit is kilojoule per kilogram times degrees Celsius. And maybe I'll give you like 30 seconds because this is quite straightforward. I guess many of you have learned it in physics. Okay, let's go through the answer. So this is the equation that we'll use. This is the sensible heat calculation equation. The heat is equal to the amount of water, M, times the specific heat, times the temperature difference. And then we just plug in the numbers. Okay, so 10 kilogram times 4.2 kilojoule per kilogram and the degree Celsius times final temperature 100 degrees C, initial temperature 25 degrees C, and make sure that the unit can be cancelled, right? If you have a kilogram here and a kilogram here, so some cases the specific heat is given in the unit as joule per gram. In that case, you have to be very careful. Make sure the unit can be cancelled. So just plug in number and you get 3150 kilojoule. Okay, very straightforward. Any questions about the calculation? Okay. And then this is the question to calculate the latent heat. Same thing, it's 10 kilogram per water and at 100 degrees C. So basically we're converting liquid, 10 kilogram per liquid in liquid water into 10 kilogram of gas steam of water. And assuming that the latent heat, specific latent heat is 2257 kilojoule per kilogram at this temperature. So I'll give you maybe a few seconds to think about because it's also very straightforward. Okay, so we just plug in the number, right? The QL, the heat of latent heat, is equal to the weight, the mass of the water times the lambda is the specific latent heat. So just multiply these two numbers, and it's 22,570 kilojoule. Okay. So one thing, I'm not sure if you guys noticed that the latent heat here is much greater than the sensible heat, right? So it's saying we're both processing 10 kilogram water, and it only costs 3,000 kilojoule to heat the water up from 25 degrees C to 100 degrees C. And afterwards, it takes 7 times more energy to evaporate this amount of water. So this is quite a drastic difference between their magnitude. So this question is basically combining the two part, the sensible heat and latent heat calculation together. Basically, we want to convert 15 kilogram of the water at 25 degrees C is what we started with. And we want to heat it up to steam, 15 kilogram of steam at 120 degrees C. And all the numbers are given. So we give you the specific heat of water, 4.2, specific water vapor, which is the steam, is 2.0, and the specific latent heat, 2257. And want to calculate how much is total energy that is needed. So this question is a little bit, we just need to combine what we have done, right? So I might give you like 1 minute. If you are done, just raise your hand and let me know, and let's check the answers later. Anyone got the answer? Or at least you know how to do it? How many parts of heat do we need to calculate from here? Any thoughts?
You're probably gonna have 2 parts. One from when you're doing sensible heat from 25 to 100, and then one from when you're going 100 to 120.
So Chris, so are there 2 sensible heat or just 1 sensible heat?
2.
Okay, that's right. That's right. So we will have to calculate 3 segments, right? Okay, so let's check the answer. I believe many of you have got it. If you confused about the calculation, just come to my office hour. I can certainly help you. Because in the last midterm, I found that some of you are struggling with the d-value, f-value calculation. And I think because that's part of the problem with the remote, the virtual lecture, because it's in class lecture, it's I expected that I got more good correct answers in those questions. So if you have any confusion, just let me know, okay? So the first part, stage 1 is to increase the water temperature from 25 degrees C to 100 degrees C. And so we use the sensible heat calculation, right? And plotting numbers, 15 kilogram, 4.2 temperature difference, and we get the first amount of energy that is needed. And then stage 2 is to convert the water to vapor, right? So the second equation, we use the latent heat equation, 15 kilogram times 2257. So we got 33,855. So remember, this number is always much greater than the sensible heat. So this is something that you can use to check if your answer is near in the correct range or not. Sometimes if you got their answers very close, or even the first energy is greater than the latent energy, then probably you have to do some recalculation to verify your answer. So this is just to give you a sense of how their magnitude are different. So that's stage 2, right? So we basically converted all the water from liquid to gas, but the temperature didn't change. And then in the stage 3, we increased the steam temperature from 100 degrees C to 120. So again, we use the sensible heat, the heat equation, right? So plug in 15 kilogram, and then be careful here. The specific heat of the vapor is different. Okay, so we give you the vapor specific heat is 2.0. Okay, so in this case, you get 600 kilojoule. So, and then finally, you just add all the energy together, and it's 39,180. I believe many of you should have got this number, right? If you didn't, okay, Christine got it. Okay, this should be, okay, Chris got it, good. So this is a general rule of thumb. Oh yes, Delaney, you have a question?
Oh, I did that on accident.
Okay, okay, great, good job. So here, whenever you see this type of question, the way that you will never miss any part of energy is that you plot out the diagram, right? So once you plot out, you will clearly see that there are 3 stages. So even though sometimes if you are solving a realistic problem, that it's always good to plot it out. So in that case, you won't miss anything, any piece of the calculation. Okay, awesome. So, okay, I'll talk about the percentage of the energy used later. Okay. So as we talk about, we have single effect evaporator, right? Which means there's only one chamber that we use. The steam the steam will coming from the top, and then to heat up the product. But the vapor from the juice is no longer used. It's just exhausted, or is or just we wasted. But as you know, the vapor carries a lot of energy. So if we use a multiple effect, those vapors can be reused and to generate a higher energy efficiency. So, and typically there's a vacuum pump to help the separation of the vapor at a lower temperature. So this is typically a design of a single effect evaporator. And so since I always talk about the energy efficiency, but we need a value to define what it is, right? So in our first couple of weeks, when I briefly mentioned there's a terminology called steam economy, but I didn't go through too deep. But here I want to show you what is steam economy defined. So steam economy, as you can see the equation, it is equal to the weight of the water evaporated from the product divided by the weight of the steam that has been used. So for example, if we have removed the 1.3 kilogram of water from the foods using 1 kilogram of steam, that means our steam economy is 1.3. So this number basically means one unit weight of steam can convert how much foods. So the more food that you convert, the greater energy efficiency there will be, right? So this number, if it's larger number in steam economy, that means this system is more energy efficient. Does it make sense? Okay, so for the typical value of the steam economy for a typical single effect evaporator is close to 1, which is reasonable because it's like steam exchange, right? We exchange the energy from steam to the energy to the evaporation. Basically, it's like an exchange of the latent heat, right? So one portion of latent heat gets one portion of the latent heat from food product, right? So typically it's close to 1 for the single effect evaporator. However, when we connected those single effect evaporator together using those pipes to reuse those steam or the vapor from the products, the steam economy can be boosted to 6 to or to even 6.5, which is many times higher than the single effect evaporator. So actually in 330, FSN 330, you guys will be able to calculate the steam economy in a multiple effect evaporator. But here I just want to show you the definition of them, the steam economy, and how different is the multiple effect evaporator compared to single effect evaporator. Basically, you are saving 4 to 5 fold of the energy, right, to reach the same percentage of the water removal, which is huge saving of the energy. Any questions here? All right, so so after talking about the steam economy, I'll briefly introduce you different types of evaporators. So in this class, we'll go through the batch type evaporator, natural circulation, forced circulation, racing film, and the falling film. So batch type evaporator is the most common one. It's like our kettle, but there we have a condenser to separate the condensed products and to separate the vapor. So this is a very very simple one. And if you guys, I believe if you look at the diagram, you'll understand, right? So the food product will be boiled here, heated up by steam, and the product, once it's concentrated, will be removed. So it's a batch process, and the vapor will be collected by the condenser. Problem is that it takes a long time because think about the boiling of water, right? It's so slow, and the capacity is very low. So that's why that in the industry, we use much more advanced evaporator to replace this. So one of the upgrade is called a natural circulation evaporator. So if you look at this diagram, basically we have a steam. This is to heat the product, and the product is, there's a feeding inlet, but it's not labeled here. But the product is basically circulating this system, and the circulation is driven by the convection. So remember that the convection is something, when we heat up a food product, then when the density, there's a density gradient where the low density portion, which means the high temperature part, will raise, and those low temperature portion will drop. So that will naturally form a circulation. Okay, and there is a separating vapor valve. Basically, there's a condenser or vacuum to kind of pour out the vacuum, pour out the vapor, and this system, although it's a little bit more efficient than the batch process, but still it's very slow because the circulation by convection is, the rate is still limited, right? For example, the velocity of the product in the tube is 0.3 to 1 meter per second. Probably you don't have any sense about how quick it is, but when we talk about later other evaporator, there's a very distinct difference between how the liquid moves here. Okay, so forced circulation. So this is something that very similar to the natural circulation. So natural circulation, everything is driven by the natural force convection. But in the forced circulation, we actually just installed a pipe here. So with the pipe, the moving of the water can be speeding up. And if you look at the velocity, it's 2 to 6 meter per second, which is much faster than the 0.3 to 1 meter per second, right? So in that case, the residence time can be much shorter, and the system has been used to evaporate tomato juice to produce tomato paste. Okay, so forced circulation evaporator. Also very simple, but just with a pump.
So it's not as important for them to be like super liquid, like low viscosity liquids in this one?
In this one, it doesn't have to be because we have a pump to push it. So, but this one, the natural circulation, it has to be low viscosity, right? Because the moving around is driven by the self, right? So in our canning report, we found that the convection is so limited in those high viscosity foods, right? So the convection is probably not good here, but the forced circulation, we can use it to process high viscosity food because we have a pump to push it, right?
Okay.
Good question. Good question. Okay. So the next one is the racing film evaporator. This one is a little bit tricky because it's hard to explain and hard to understand. But Dr. Paul Singh, I showed you some of his video before. He is very good at explaining those very kind of abstract or a very complex system. So I will just let him to explain, then I'll do a quick summarize. Okay, let me share the sound.
Involves long vertical tubes, typically 5 to 15 meters long and 2.5 to 5 centimeters in diameter. These tubes are placed inside the steam chest, where the liquid inside the tubes is heated from the outside by condensing steam, as we see in this animation. As the liquid at the bottom of the tube heats, bubbles will form that rise inside the tube at high velocity. So typically we have slugs of liquid and bubbles rising rapidly to the top of the tubes. The velocity can be very high, up to 100 meters per second. The liquid and bubbles then exit at the top, and often upon exit they hit baffles to break up any foam. This type of evaporator is used mostly as once through. That means you allow the product to go through the tubes only once, although sometime recirculation is also used. One gets very high heat transfer coefficients in this type of system. A rising film evaporator is used in the manufacture of condensed milk.
Okay, so what do you think is the main difference between the racing film evaporator and those we have talked about, the forced circulation and natural circulation evaporator?
This one really doesn't focus on the circulation factor.
Exactly, Chris. So yes, that's why that's this racing film and the falling film we'll talk about later is way much more efficient because previously, if you look at those forced circulation and the natural circulation, basically we have the same liquid that is moving through the system for a long time. And then although we are separating them in the meanwhile, but they're still, every part of the liquid has to go through the system for a long time. So which means our overall production efficiency is not that high. But assume that we can make the process into a one-time pass process, the efficiency will be way much greater, right? So that's their main difference. So that's why that the racing film is way much more common in the industry. And it's part of the reason that when you see those huge um, towers in those chemical production pilot and the food production pilot, those are all the evaporators. They had to be built in a very high. You see, it's 5 to 15 meters long. So in that case, we can make sure that one time pass is good enough to remove the desirable amount of water that we want. Okay, and you can see that the velocity at the top can reach 100 meter per second. Right? Remember the first number that we have seen, it's 0.3 to 1 meter per second. So this one is like hundreds times more faster in water removal. And it also has high heat transfer coefficient, right? Because it's like during the contact and during between the steam and the food is based on the heat exchanger, right? So it's more efficient. Okay. And this is the falling film evaporator, which is about very similar in concept. Instead of the liquid moving up, in the falling film, the liquid is moving down. And let's again watch this video. Let's see.
In falling film evaporators, long tubes of diameters from 5 centimeter to 25 centimeter are used. The liquid feed enters from the top, and the liquid flow inside the tubes is by gravity. But the design gets complicated to get a uniform distribution of the liquid as it flows down inside the tubes. To obtain improved distribution of the flow, distributors are used. Also, sometimes spray nozzles are used to minimize any non-uniform distribution of the liquid feed. The falling film evaporators can handle more viscous products than the rising film evaporators, because here now the flow is mainly by gravity. Typically, heat-sensitive products such as orange juice concentration is done in these types of evaporators. The typical residence time is fairly short, anywhere from 20 to 30 seconds, in comparison to 3 to 4 minutes in the rising film evaporators. There is another variation of an evaporator design that involves a rising film section in the beginning part of the evaporator and then a falling film section in the second part of the evaporator, as seen in this animation. So the liquid feed first goes through the rising film section where the feed gets pre-concentrated, and then it is allowed to fall by gravity in thin films in the falling film section of the evaporator. Again, these types of variations allow use of these evaporators for specific applications for heat-sensitive foods.
Okay, so basically, the only difference is that the direction of the liquid moving, right? So instead of moving up, it's moving down. Okay, so it's better for viscous food, right? Like orange juice, and because the residence time is much shorter, so if we have something that is too diluted, probably within this time period, it's not good enough, right? Because if we talk about a racing film, the liquid moves up much slower because we can control how fast it moves up. But in the falling film, basically everything just drops. So if it's not completed, it can still drop to the outlet. So that's why there's like a combination of the rising film and the falling film. So the rising film basically can condense the product to a certain level, and it becomes quite viscous, and which is becomes suitable for the falling film. Okay, so there's a specific design needed to make sure that the liquid is evenly distributed in different tubes, right? Because if we connect it into a pipe directly, then we have in the center we will have larger flow, and on the sides we'll have smaller flow rate due to the fraction. So in that case, the product might get burned on the side and then not completed in the center. So that's why we need a very specific distributors. So there are several ways we do distribution in the falling film, like static distribution. Basically, it's like a tank that we fill the water, and then the tank will distribute those liquids through those holes. And sometimes we use nozzle spray to control their distribution. So this is just a video to show you that there's no background sound here. So I'll explain what happens to you. So this is a falling film evaporator, right? In the bottom, you'll see a lot of tubes for the heat exchange. And here's a tank where the food product can be stored for temporarily. Okay, so there's always like a tank, and then below the tank, there are different there are holes open, and those holes will be able to distribute the liquid evenly into different tubes in the falling film heat exchanger. So that can help us to make sure that the product is produced uniformly or homogeneously in the evaporation system. Any questions about the falling film evaporator?
So what
I have a question.
Yes, go ahead.
I guess I'm confused with the spray nozzle type of, yeah, that one.
Yeah. So the spray nozzle, it's pretty much like a spray drying. Actually, the spray nozzle is used not that often because even with spray, the distribution it's hard to control it evenly. So right, so but this is one of the way to control the flow distribution though. Do you have any specific questions, or you just don't have idea how that works, Sarah?
Yeah, I didn't really know how it worked, but this helped.
Okay. So it's pretty much like spray drying, right? I showed you guys the spray dryer nozzle, right? It kind of distribute water with the air and the mix with air, and the air kind of dry it momentarily.
So even with like more viscous liquids, the spray nozzle still works.
It has to go. So probably, Chris. I'm not sure if you know that for spray drying, those spray drying feed, they are pre-concentrated. So those nozzles is actually driven, they're powered by high pressure nitrogen or air. So they can although their opening is very small, but because the pressure of air is so high, it usually don't get clogged. And also it gets a self-cleaning function. Like if you get a chance to see one, we should have one in the pilot plant. Every couple seconds, there's a very strong pulse of the airflow that will blow through those holes to make sure there's nothing clogged there. So those nozzles are very good in handling highly viscous products, as long as there's no big particles inside there. Otherwise, other than that, it should be working very smoothly. Any other questions, Christine?
Yeah, for the falling film, does it work at a lower temperature than the rising film? Because it said that it was better for heat-sensitive products.
Yes, actually the temperature of the heating medium is the same. The only difference is that the residence time is much shorter. So probably if you recall from Dr. Pausing's video, the residence time here is just 20 seconds. Basically, how long it takes to fall down, basically it's a residence time. But for the racing film evaporator, the residence time goes to 3 minutes or so. Basically, you have to, because when the liquid is moving up, the volume keeps decreases, right? Because the water keeps evaporating, and then once it volume decreases, and then actually it kind of slows down the movement. So it's better to reach a completely evaporated product, but it's definitely the temperature will go much higher than the falling one, because the residence time is it takes much longer time to travel through the tube. Does it make sense?
Yeah.
Okay. Okay, any questions before we move to the next section? Oh, there's a chat box, almost missed. What is the residence time like?
It got covered in the second video.
Okay. Good. Okay. So we'll do a little bit of the mass balance. I will try to keep it very simple for this 204 class. Okay, so the mass balance, just to help us to understand a very basic calculation. So as you know that we have two inputs, the steam input and steam come out, and we are not going to calculate that, because the steam goes it goes into a individual or separate independent system. So it doesn't have any interfere with the food. So that's why how much steam that we put there, we always will have the same amount of steam come out as condensate. But for the food part, when we input a dilute liquid, and then there are always two outputs, right? There is a vapor output, and there's a concentrated product output. And we use several terminology or parameters to describe how fast we feed it and how fast we can collect the product. So here you can see that the MF dot if you see some any figure or any any letter with a dot on the top, it means the rate. So mf without a dot means the mass of the feed. Okay, but if there's a dot, it means the mass of the feed per unit time. Okay, so basically this is a rate rate parameter, and x value is the solid fraction. Okay, and here as well we have MP, which is the product rate of the concentrated food product, and XP is the solid content, solid fraction. Okay, and same here, MV is the production rate of the vapor. And I'm going to discard all the temperatures because we are not going to do any energy balance here. It's too complicated. Okay, so if we write down the mass balance equations, there will be two equations, right? There will be a total balance of the food product. How much food we feed, MF, is equal to how much food comes out, MP, and how much vapor generated, right? Is that understandable? Okay. And in the meanwhile, we'll have a solid balance, right? So basically it's how much solid we put there. Okay, XF is the solid content fraction and XP is the solid content fraction in the product. So MF XF is the solid in the feed, and MP times XP is the solid in the product. So they should be the same, right? Because no solid will go to the vapor. Okay, and also we have water balance, how much water that we feed in equals how much water it comes out, right? So water goes two portions. Part of them goes to vapor, right? And part of them remain in the product, right? So this is the description of each terminology. So we use the unit kilogram per second here, but you can always, as long as you use the same unit, it shouldn't matter. So any questions about those equations? Okay, so we'll do a quick practice. Okay, and this is just a energy balance, and just for information, because we learned about all the heat, latent heat, and the sensible heat. But I'm going to remove this energy calculation from here. It might be too complicated. So here's an example for you to practice to calculate the mass balance. So if we have a tomato juice, we are concentrating it using the evaporation system. So when the system goes steady stage, the diluted juice is fed at 0.8 kilogram per second, which is the MF dot, right? And then the solid concentration is 11%. And after concentration, the juice will come out at 70% in solid concentration. And we want to calculate what is the mass flow rate of the concentrated product and how much water vapor will come out through from the evaporator. So this is what we are given. Okay, I just listed it for you so you can, it might be easier for you to calculate. Okay. I'll give you maybe 1 minute to think about, and if you finish, let me know. If not, I will go through this question together. Okay. Ready? Okay, let's go through this question together. So it's given that we know the feeder flow rate is 0.8 kilogram per second. We know the concentration 11%, right? And then we know the final concentration 70%. So we use the solute balance, right? How much solid we feed in equals how much solid comes out, right? And then we just plug in number, 0.8 is MF, 11% is XF, and then for the MP is the final product weight, right? Flow rate, and then we know its concentration 70%, right? So it's just one step calculation, and then we'll get the flow rate of the final product is 0.13 kilogram per second. Okay. Any questions? Okay. Okay, so this is a very simple one, right? And then if we want to calculate how much water vapor comes out, we use the total mass balance, right? How much feed we put in equals how much product we get and how much vapor is removed, right? And then also we just plug in numbers, right? So 0.8 is our feed and the 0.13 is the product we collect, and the rest of them will be the vapor. So we got the vapor 0.67 kilogram per second. Any questions? Cool, it should be very straightforward, right? So I assume many of you should know how to do this, right? So just simply list these two equations and see what you have and calculate those unknowns. Okay, so because we are kind of running late, I will leave this question to you. I'll put it into the assignment question. Okay, so basically it's all the same thing. I just changed a few numbers. Okay, so just for you to practice in the assignment. And quick summary. So this class, we focused on the thermal concentration of food, which is the evaporation, right? And then we covered what is the sensible heat. Basically, it's heating water without a phase change, right? And the latent heat is the thermal energy involved during the phase transition, right? And the latent heat is always much greater than sensible heat. And third, we didn't cover this. I'm sorry, I should have removed this. And also we talked about the single multiple effect evaporator, right? And the different operation principles in different types of evaporators. We talked about the batch evaporator, the most basic one, like our kettle, right? Then the natural circulation, forced circulation, they're all circulating pumps, all circulating evaporators, right? And then we have racing fuel, okay, which takes a little bit longer, but can reach more concentrated products, right? And the falling film, it takes shorter time, okay, but it's good for viscous foods. So 5 evaporators, they're very different. And finally, we learn about how to do the mass balance. Okay, it's just a very simple math, but you just need to draw out the entire evaporator and you know, maybe draw an arrow and try not to miss any part. So that's the key, because the calculation should be very straightforward, right? As long as you plug in the number correctly, then you should get the answer. Any questions about this lecture before we finish? Okay, then guys have a good weekend, and so I will give you more information about final, and next week we have a few dues, so please do not miss it, and I'll see you next week.
Thank you.
Thank you.
Thank you.
Thank you.
Thank you.
Professor,
Yes.
Bye, thank you.
I had just more of like a curiosity question.
Yes.
What is the difference, like if there is any, between the evaporated milk and like the condensed milk in like a processing standpoint?
Oh yes, that's a great question, Chris. So there's a water concentration difference, but I need to check the exact numbers. There's like a dehydrated food, it has to reach 2.5. So there's a certain regulation that in terms of that. You can also look it up. I don't have an answer right now because I used to, I think I remembered, but later on I forgot. But that's a good question. I think I should have mentioned in the class, because that's kind of the criteria to define evaporated food and the condensed food.
Okay, yeah, that makes sense. That's mostly what I was just curious about, like if there was any reason for like the different wording, or if it's just a marketing gimmick or something like that.
Yeah, I need to. I'll check it out, and I'll probably send you an email afterwards.
Okay, cool.
All right. See you.
Thank you.
Bye-bye.
Yeah, have a good weekend.
You too.